Hi, and welcome to 9.3 Elastic Collisions. This is the start of the Law of Conservation of Momentum videos. We have elastic collisions, inelastic collisions, and then we do recoil and explosions. The Law of Conservation of Momentum simply states that your initial momentum is equal to your final momentum before and after some kind of collision. So in these examples, you have two balls coming together and they hit each other, and then after they hit each other, after the collision, they might have some different velocities. But when you add up their total momentum, this one plus this one, that's the total initial momentum. And then you have this one and this one, that's the total final momentum. The total momentum is going to be the same. It's conserved. It stays the same. It doesn't change. All right. So the initial total momentum is the combination of the momentum of A plus the momentum of B. And we know that the momentum is equal to mass times velocity. So you have the mass times the velocity of A initially, the mass times the velocity of B initially, and you're adding those two together because it's the total momentum initially. And then the same thing on this other side. So after the collision, you have the mass of A times the velocity of A after the collision. So most of the time you're changing your momentum because your velocity is changing. So you have the final momentum of A plus the final momentum of B, and you're adding those together because it's the total momentum, and they're equal to each other. Momentum is conserved. So that's the law of conservation of momentum. So for these problems, we want to find the missing information using the law of conservation of momentum, and then we're going to show all the work and include formula and units. So for the first situation, we'll call this, this is the first ball and this is the second ball. Before they hit, and then they hit each other, and then it's the first ball and the second ball. So we don't know what the initial velocity of, oh no, we should actually call it A and B, right? Because this is as VAI. So let's call that A and B. So we don't know the initial velocity of ball A, but we do know the mass of A. It's 10 kilograms. And we know the initial velocity of B. It's 3 meters per second. And we know the mass of B is going to be 3 kilograms. Now, after the collision, the velocity of A, they tell you, is 4.2 meters per second. And the mass of, they all stay the same. And the velocity of B after the collision is going to be 9 meters per second. So we know pretty much all the information except for the initial velocity of A. And we're just going to use this formula here that we talked about before. Now, it's kind of hard to, some of my students, they have difficulty writing out the subscripts as you write the whole equation because it gets a little bit confusing. So what I found was to just visualize what is actually happening. You have the momentum of A plus the momentum of B. So you have a mass times a velocity plus a mass times a velocity. And that's what we just write down for now. And then after the collision, we have another mass times velocity and another mass times velocity. They're separate entities still. So we'll write them like that. And now we want to be organized because it's just mv plus mv equals mv plus mv. We want to be a little organized and write in our subscripts. So this is for A. This is for B. This one is for A. And this one is for B. And we want to specify that this is the initial velocities on this side of the equation, and this is after the collision. This is the final velocity. And that's, I find that's might be a little bit easier to write out that big long equation if you try to do it that way. And you could also kind of visualize conceptually what it all means instead of just trying to focus on writing the correct subscripts in the right spot. I'll try to show you what I mean in the next problem. I'll do it the way that I used to do it. So we'll just plug in now. This is 10. We're looking for the initial velocity of ball A. This one is 3. This one is another 3 meters per second. And after the collision, the mass of A stays the same, but now it's moving off at 4.2 meters per second. And the mass of B stays the same, but now it's moving off at 9 meters per second. So this is 10 VAI plus 9 equals 42 plus 27. So 42 plus 27, that's 69, and this is 9. This is 10 VAI still. And then you subtract 9 from both sides, so you have 10 VAI is equal to 60. So the initial velocity of ball A is 60 divided by 10, 6 meters per second. So this is 6 meters per second. And now this diagram might look, it might make more sense, because it's like, well, is there a collision there? But they're both moving in the same direction. Yes, they're both moving in the same direction, but ball A is going faster, as we just calculated. It's going at 6 meters per second. This one only is going at 3 meters per second. So ball A catches up to ball B, gives it a nudge, transfers some momentum, makes it go faster, makes ball B go faster. Ball A loses some momentum. It's going slower now. So the momentum transfers from ball A to ball B, but the total momentum on both sides is the same when you add them together. The momentum of A plus the momentum of B is a constant before and after the collision, because momentum is conserved. All right, number 2. A little bit trickier. Let's try to write our givens and our unknowns. Typically, so this is A and B. This is A and B. Typically, I write the masses first. So the mass of A is 3 kilograms. And the mass of B is going to be 2 kilograms. And then we start talking about the velocities, because the mass doesn't really change, but the velocity of A initially is 3 meters per second, and the velocity of B initially is 2 meters per second, and the velocity of A after the collision, we don't know what that is, and the velocity of B after the collision is 4 meters per second. Now, I'm going to pause it here. Hold on a second. I think I just made a mistake. Hold on a second here. You got to check when you're writing your velocities, is velocity a vector or a scalar? You should know this. Velocity is a vector quantity. It has magnitude and direction, which is shown in this diagram by the arrows. These are hints. So, oh yeah, velocity is a vector quantity. The direction matters. And so is momentum. Momentum is a vector. So when you add up the momentums, if you have a momentum going to the right, and then you have another momentum going to the left, they kind of like cancel each other out a little bit. It's not like you have this momentum going this way, and now they're going to speed up. No. You have 2 meters per second to the left, so you should think of it as negative 2 meters per second. It's negative 2 meters per second. So you got to be careful when you're writing your givens and your unknowns over here, and you're looking at your velocities, or maybe in the problem it tells you that the velocity is west, or it's moving to the left. You have to be careful and remember that velocity is a vector, so you have to make the things moving to the left or going south or down, the velocity is negative when you plug it in the equation. Now, speaking of equations, let's write it down. I'm going to try to do it the way I used to do it, which is kind of confusing. You have to try to keep your subscripts straight, and you're just more focused on writing down the subscripts correctly. So first we'll do the mass of A times the velocity of A initially, plus the mass of B times the velocity. So yeah, wrote that as a script. Velocity of B initially is equal to the mass of A times the velocity of A after the collision finally, plus the mass of B times the velocity of B final. And just make sure I didn't make any mistakes. All the I's are on the left, all the F's are on the right. AA, BB, AA, BB. Okay. Yeah, this makes sense. All right. So you could write it out either way. I mean, it's really up to you, but I think writing MV plus MV equals MV plus MV, and then you write in the A's, and then you write in the, that whole thing, I think that makes it a little bit easier. Okay, now that we have the equation written down, we could start plugging in. So the mass of A is 3, velocity of A initially is 3, plus mass of B is 2, times the velocity of B is negative 2, -2, it's going to the left. So this is 3. This is, we don't know what this is, VAF. Plus this is 2. And the velocity of B final is 4. Okay, now everything's plugged in. Do some math. This is 9 minus 4 equals 3 VAF plus 8. So 5 is equal to 3 VAF plus 8. Subtract 8 from both sides. So you have -3 is equal to 3 VAF. So the velocity of A after the collision is -1 meters per second. And your diagram shows that. But, you know, in other problems, if you didn't have a nice diagram showing you the direction of the velocity after the collision, it doesn't have to show you even the direction. It could just be like, what is the velocity? And then if you get a negative number, you're not wrong. You're just showing, oh, the ball comes in and then it bounces off, and the negative tells you that. So it's like the math is telling you what is going on, a picture in your head of a physical thing in the real world. That's why physics is the best, because not only is it fun math times, but it's also like representing real things. Okay, so number 3, we got the main thing was if it's to the left, you got to make it negative. That number 2 is a key one. If you got it wrong, maybe that's why. So number 3, let's call it A and B again. So this is A. This already has MB, A, B. Okay. Are you looking for the mass now? That's going to be a little bit weird. Let's try that out. And so we know the mass of A is 3 kilograms. We don't know what the mass of B is, but we know the velocity of A initially is 6 meters per second to the right, and the velocity of B initially is 4 meters per second to the right. So we don't have to worry about negatives. And after the collision, I'm running out of room, so I'm just going to write it over here, is going to be 3.5 meters per second to the right, and this is going to be 5.5 meters per second to the right. Okay, now let's write the equation. So I'm going to do the thing again. They're separate. They don't lock together yet. That's inelastic collisions. When they lock together, and the equation looks a little bit different. But right now, separate things, so you have 4 terms, and it's kind of nice. It's 4 different momentums that you have to add together. Is the initial equal to the final? It's kind of like a nice thing with the law of conservation of momentum. That's what it's all about. So this is A, B, A, B. This is the initial velocities. These are the final velocities. Okay, this is 3 times 6 plus, we don't know B. We don't know the mass of B, but we know it's moving at 4 meters per second before the collision. After the collision, the mass of A is moving at 3.5 meters per second, and the mass of B, we don't know it. Oh man, there's 2. Oh wait, but it's like the same unknown, but it's written there twice. So this is going to be 5.5. All right, so now you have to solve for, it's like solving for x, right? But now we have 2 variables, but they're the same variables. So we might have to combine like terms, that type of thing. Yes, very good. So this is going to be 18 plus 4mb is equal to 10.5 plus 5.5 mb. Now, you have to combine like terms. You can't just do 10.5 plus 5.5. You can't do it that way because 10.5 doesn't have an MB. It's not being multiplied by MB. 5.5 is. So those are not like terms. So back in the day, I'm sure your algebra teachers did this. It's like, okay, circle the ones without the MB. Very good. And now circle the ones with the MB. Okay. So you got to put the blues with the blues and the greens with the greens, because the greens have this MB term and the blues don't. So maybe they used circle, maybe they circled them and put a square for the MB, you know, whatever it is. It's a technique that teachers use. It's kind of good. All right, so let's subtract minus 10.5. So that cancels out, and you get 7.5. And then we could write the whole thing plus 4mb if you really wanted to, but I'm kind of lazy, so I'm just going to go ahead and subtract 4mb from both sides. Okay, so 7.5 is what we're left with on this side of the equation, right? So 7.5 is equal to, that was canceled out, the 10.5, so you have 4.5 times mb. 5.5 minus 4 is going to be 1.5 mb, and now you just have to divide by 1.5, so the mass of B is going to be equal to 5 kilograms. Okay, pretty good. So the trick for this one again was you had to combine like terms to solve for mb, the mass of B, and there you go. Now, on the back sheet, there's no more diagrams to help you, so you have to really be careful when you're writing your givens and your unknowns. Most of the time, there won't be a diagram. So it says a billiards ball, which we'll call ball 1, has a mass of 0.2 kilograms. So the mass of 1 is 0.2 kilograms. And it's traveling to the right at 6 meters per second. So the velocity of 1 initially is 6 meters per second, and then it strikes another billiard ball, which is ball 2 of equal mass, so m2 is equal to 0.2 kilograms, and it's of equal mass, also traveling to the right at 3 meters per second, so velocity of 2 initially is 3 meters per second. After the collision, ball 1 has a velocity of 2 meters per second to the right, so this is the velocity of ball 1 after the collision. The final velocity is 2 meters per second to the right. This is all to the right? Just double check. So this is right, right, right. All right, so we didn't have to make anything negative. We didn't forget to make anything negative. Everything's positive. It's moving. The balls are moving to the right. And we're looking for the velocity of ball 2 after the collision. So you write out your equation. The momentum of the two separate balls, and then they strike each other, and now the balls have different momentums that we need to add together to get the total momentum. So this is for, I did A's again. This is 1, this is 2, this is ball 1, this is ball 2, this is the initial velocities, these are the final velocities. Beautiful. All right, let's plug in. So this is 0.2 times 6 plus 0.2 times 3 is equal to 0.2 times 2 plus 0.2 times, we don't know, V2F. All right, so 0.2 times 6, that's 1.2 plus 0.2 times 3 is 0.6 is equal to 0.2 times 2, 0.4 plus 0.2 V2F. All right, so 1.2 plus 0.6, that's 1.8 is equal to 0.4 plus 0.2 V2F. And now you subtract by 0.4 on both sides of the equation, so you get 1.4 is equal to 0.2 V2F. And now you divide both sides by 0.2, so V2F is going to be equal to a nice 7 meters per second. All right, number 5. Number 5 says cart A of mass 5 kilograms. So the mass of A is 5 kilograms. Moving at 20 meters per second. The velocity of A initially is 20 meters per second. It collides with a cart B of unknown mass. We don't know B again. So it's like number 3. Moving at 10 meters per second in the same direction. All right, so it doesn't necessarily say left or right, but it does say it's moving in the same direction. So we have to make it, we made this positive, so we better make the velocity of B also positive. This would work out if you make them both negative. It's just that you're assuming they're moving in the negative direction. But we're making it positive just because we want to be positive people. After the collision, cart A moves at 10 meters per second, so the velocity of A after the collision is 10 meters per second. And cart B at 15 meters per second, so VBF is 15. Both still in the same direction. That's nice. What is the mass of cart B? Okay, so we have the mass of the momentum of A plus the momentum of B is equal before the collision is equal to the momentum of A plus the momentum of B after the collision. Hopefully by now you kind of get the idea with how to set up this equation. It is a long equation, but luckily, you know, it's only two objects every time. We're not doing objects with equations with three objects or anything, so it looks the same, but you have to understand the concept and why we're doing what we're doing. Plus, this is what we're looking for. This is 10. This is 5. This is 10. This is what we're looking for. And this is 15. All right, yeah, I mean, like, you could also just make a little mistake when plugging things in. There's a lot of things to plug in, so I could see making an error like that. So you just want to make sure you check your work. So this is going to be 100. So the momentum of A is equal to 100 plus 100 kilogram meters per second. We should be specific, plus 10 MB. That's a weird looking B is equal to 50 plus 15 MB. Now, last time, if you remember, I kind of did it all in one step because I was running out of room. And as much as I would like to do that, some people have trouble with the algebra, so I'll slow down a little bit and I'll do it in like multiple steps here. So that cancels out. You're left with 50 plus 10 MB is equal to 15 MB. All right, now we really have to combine like terms. So we're subtracting 10. Oh man, MB from both sides. Oh man, I wrote an equal sign there instead of a subtraction sign. All right, that cancels out. You're left with 50 on the left side of the equation and 5 times MB on the right side of the equation. So you divide by 5. So the mass of B is going to be 10 kilograms. Very nice. Yeah, so we were just combining like terms. If you skipped ahead to this one, I did the whole thing. I kind of skipped over that, but this and this, these two are like terms because they're not being multiplied by MB. This is being multiplied by MB, and so is this one. So you have to combine those two. You cannot do 100 plus 10 and say 110 MB. That is not what you're doing here. These are not like terms. There's no MB on this side here, people. Come on. I see it all the time, though, so if you fall into that mistake, just try not to do it, all right? You can't just combine like terms when you're adding and subtracting, right? Sorry, you cannot combine unlike terms with an addition or subtraction sign. You have to get these guys together, and then you have to get these guys together over here, and now you could divide out that number and get the mass by itself. Very good, very good. Number 6. 6 says a 5 kilogram cart moving to the right at 6 meters per second makes a head-on collision with a 3 kilogram cart moving to the left at 5 meters per second. So let's call the mass of cart 1 is 5 kilograms. And the initial velocity of cart 1 is 6 meters per second. And the mass of cart 2 is going to be 3 kilograms. And it's colliding head-on. It's a head-on collision. And it's moving to the left. It even tells you it's moving. It could just say head-on collision. But it specifically says that cart 2 is moving to the left. So it's moving at 5 meters per second. And what do I have to put here, guys? What do I have to put? It's moving to the left. This one's moving to the right at 6 meters, so that's positive. This is moving to the left. It's got to be negative. Come on. If you're watching this video right now, it's probably for this problem. You probably skipped right over here because you didn't get the right answer. Because you didn't, I'm guessing you didn't put the negative sign. But you know what? Watch the rest of the video, because then I get more views. Okay, so after the collision, the 3 kilogram cart, which we called 2, maybe that's another trick. All right, after the collision, the 3 kilogram cart moves to the right at 2.5 meters per second. So they're telling you V2F. All right, because it's that we called the 3 kilogram cart M2, and it says after the collision, the 3 kilogram cart moves to the right. So after the collision, this is moved to the right at 2.5 meters per second. So that's kind of like an added in little trick just by the way they kind of worded it. Or, you would think that they would tell you what the 6 kilogram cart is, because that's the first one they said in the beginning. But so maybe you fell into the trap of calling it V1F. And if you called the 5 kilogram cart, it's not V1F. No, they're telling you the 3 kilogram cart is moving. All right. Hopefully you guys get the point. So there is the added trick in there. You think, oh, I'm really confident. Oh, I put the negative sign for the left. That's very good. But then maybe you messed that up. So that's another issue. It says, what is the magnitude and direction of the velocity of the 5 kilogram cart after the collision? So they're looking for the 5 kilogram cart. So in case you didn't pick it up the first time, they're actually helping you. Like, okay, we're specifically asking for the 5 kilogram cart. Hopefully you didn't write in V1F is equal to 2.5. That's what you don't know. Okay, anyway, let's plug in. You guys already know how to write the equation, so I'll skip over that part for you. This if you're still not if you're like, oh man, I really don't know how to write that equation, it's super long. Go back to the beginning of the video. I kind of explained 2 different ways that you could write the equation down there. So the other part is you have to make sure you plug in everything correctly. Take your time, double check to make sure you're plugging in what you need to. And by the way, if you're not writing out everything on the left side like I do, especially for this unit, this really helps, guys. I mean, you're plugging in all this stuff. It's super easy to make a mistake. If you're just trying to, some kids just read the problem and try to write it. They don't even write the equation. How do you guys do that? I don't know, but I mean, sometimes it works, but you're just setting yourself up. You're going to make a silly mistake, I bet, one time. I mean, I don't know. Maybe you're smarter than I am. I mean, you probably are. But I need to organize myself here. Write out all your givens here. Write the equation, and now you're just plugging. Okay, what's that? What's that? You're looking over here. Okay. I don't know. Maybe it's just me. I feel like it makes my life a little bit easier. Sure, it's technically more writing, right? You have to write down more stuff, so it looks like it's doing more. Oh, I have to do so much more work now because I have to write down more things. But, and that is true, you do have to write down more things. But you're making your life easier. It makes it easier to do the work, right? That's kind of in life too, You got to just set yourself up nice, do a little bit of work in the beginning so that you make your life easier at the end. You work hard now and enjoy the fruits of your labor at the end. 1.5 meters per second. For example, if you have like an essay to write for your English class, you do all your work in the beginning, right when they assign you the essay, and now you don't have to cram in and try to write your essay at the last minute. I fell victim to that. I used to do that all the time though, but it stunk. All right, or how about your physics homework, or even studying for a physics test? All right, if you try to be organized and stay on top of everything, and okay, let me do my homework when it's assigned. Okay, I have a test in the end of the week. Let me start studying on Monday or Tuesday. And then it's like, oh, okay, Thursday's here. Oh, that's all right. I did all my work already. It made it a lot easier. I kind of already have a nice outline and even a rough draft of my essay. And okay, let me revise my essay. Let me just do a couple of those problems that were giving me trouble. I know there was 1 or 2 problems. This is like Thursday night before the test or Thursday before. Okay, let me tighten up the screws a little bit. Okay, I'm printing out the document. Okay, this is the morning of the test. All I have to do is like wake up and eat some breakfast, make sure I'm ready to go, make sure I get plenty of sleep the night before. I don't have to worry about studying and cramming for the test or trying to do a lot of homework at the last minute. All right, okay, super easy times. You come into the class and you sit down at the desk and you feel confident. You're just like, yes, I did everything I could. Whatever happens now just happens, but at least I can feel good about what I did to prepare for the test, and I don't have to really worry about it. Instead of like being nervous, like, oh man, I really should have studied more, or maybe you walk into class, in English class, and you don't have the essay, or you're ashamed of how bad the essay is because you did it the previous night. No, you feel confident, and you worked hard all week to do the essay, that type of thing, and then you hand it in. You do good on the test, and life's easy that way. But if you don't do the work in the beginning, you're just setting yourself up to make it harder. I mean, yeah, you could totally stay up and do all your homework. You could cram for that test, and you could do it the night before. But for me personally, I feel like it's not worth it. All right, it's better to do a little work and be responsible. All right, have a good day.